Hey everyone, thanks for coming. We'll start in a few minutes. So, yeah, if you have a little bit of um, patience, I'll see you when we'll start. I hope everyone. Sorry, I hope everyone is doing well. Hi Gilbert. Hi. First, nice seeing you. Hi Rajashi. Nice. How are you?
Hello.
Yvonne and fair-minded Bunny. Nice seeing you. I'm always happy when new people also join. Today will be really interesting. More origin of life room. So yeah, I'm really excited about this topic. So if you want to ask questions, feel free to raise your hand or use the chat for comments or questions. I will address them or read them out to the speaker here today. And I can give you a little bit of information already about the speaker. Sam Purkis, he's a professor and chair of the Department of Marine Geosciences at the Miami University. And he is, he published a lot of interesting work related to origins of life and marine geosciences. So, yeah, really happy he came. We went through some screening, like Science Society had to go through some screening by the PR department head. They kind of screened us if we are a real thing, and how we do things here. So I'm glad we passed our first real screening by university if we are a good science platform, and apparently they said okay. So that was a good moment. Hi Sam, thank you for coming. That's a very cool picture. So to unmute, it's all the way on the bottom right. There should be a microphone symbol. Yep,
Yes.
perfect.
Can you hear me?
Yes, can hear you well.
Perfect. Okay, fine. So, well, I suppose if you could just give me a few instructions, so that I will make sure that I follow them.
Perfect. Yeah, so you found that mute button. That's the most important one, or we could not hear you. You can find on the top, above our heads, basically, the link to the papers. I merged them, so I hope they are in the right order that you wanted them. And so everyone can click on them. It's not the screen share, so it's really helpful if you're discussing maybe a figure that you would say on which figure number or table number. So you are then there's a chat option, but I will monitor it for you. Like if people want to write instead of actually talk with us. That is all the way on the bottom left. There's a little number 2 on like a speech bubble. If you press on that, you're in the chat room, and then if you swipe back in the direction, then you're back here. And other than that, right now there's not too much else to know. Like, I will in a few minutes introduce you to the audience, like, you know, some just basic, like a few facts that I found on LinkedIn. I hope that's okay that I checked you out on LinkedIn.
Mm-hmm.
And then usually we ask like a couple of interview questions, and then the stage is yours to talk about your research, and we can structure it that you take questions, you know, during your presentation basically, or introduction, or we can take questions after. um
Well,
and
yeah,
yeah.
I mean, either way, but I'm totally happy to be interrupted and answer questions as they come up. That sounds fine. Hello?
Yeah, sorry, I had to go back to
Yes.
the
Yeah.
unmute button. I was sharing the room on Twitter, that
Yeah.
but yeah, yeah, that's perfect then. So yeah, we'll start in around 3 minutes. So in the
And
meantime,
how and Katrina, how long do we go for?
it's really up to you. We can usually, around an hour. If you have a little bit more time, that's also great, of course. We're always happy if people stay a little bit longer, but
Hmm.
usually around 1 hour I will maybe say, okay, now it's like the last question.
Yeah.
And yeah.
Fine. All right. Well, let's do our best.
Perfect. Sure. And yeah, I hope you had a good morning so far.
Everything. So where are you based then?
I'm in New York City,
Uh-huh.
and but I'm from Portugal,
Mm-hmm.
but I grew up most of the time in Germany, and
Okay.
yeah, and then I
Yes.
went to go abroad for my PhD, so here in the US.
Okay.
So
Yes.
I was
What is your science?
I'm a neuroscientist. I
Yeah.
was for a while at the Marine Biological Laboratory in Cape Cod. I don't know if
Uh-huh.
you know it,
I know it, yes.
but it was for neuroscience purposes. Like we worked with squids, so
Yes. Although I know they have very big synapses or so. I know they use it as a model
yeah,
organism. Yeah.
exactly. So the professor I was working with, George Augustine, he was one of, a lot of the presynaptic communicate, like how the presynapse basically starts communicating with the next neuron
Yeah.
kind of work.
Yes. Yes.
So do you like the did you visit it one time, or did you maybe
No,
the
I haven't visited it, but of course it's very famous, so I know of it.
Okay. Yeah,
Yes.
it's a cute spot. Like, it's like a cute little town, and
Yeah. Yes.
has the ferries and stuff. So
Yes. Yes.
just the winters are really,
Brutal.
yes. It was horrible. I came from Portugal
Yeah.
I did a postdoc there, and I came from Portugal into the harshest winter they had in like forever,
Yeah.
with like snow piling up in Boston that they didn't know what to do with it. The ocean froze. Like on
Yeah.
Martha's Vineyard, they had like slush. Uh,
Wow.
yeah, they had like slushy waves. Like it
Yeah.
was awful. We were snowed in for I don't know how many weeks and couldn't do much.
Yeah.
Anyhow,
Yes.
what we do for science.
Yes. Exactly.
Anyhow, I think we can start. Yeah, welcome everyone to Science Society, and of course, a special welcome here to Sam. And before we start, let me give you a short introduction. Um, so you get to know him a little bit. Sam Purkis, he's a professor and chair of the Department of Marine Geosciences at the University of Miami. And he did his bachelor's degree at the University of Southampton in the UK, and he then did a master's degree at the, I hope I'm saying it right, Vrije
Oh,
University.
the Free University, the Vrije
Oh, free.
Universiteit. It's Dutch,
Oh,
yes.
Fry. Okay, I
Yes.
should know, but I grew up so close to Netherlands. But anyway, um, they're in earth sciences and is minor in sedimentary geology. And then he also did his PhD there, um, and he majored in earth observation and geology minor, about carbonates sedimentology and sequence stratigraphy. And we are very honored to have you here, because this is such a interesting topic and fascinating, and there are still so many puzzles to solve. So thank you for coming, first of all.
Well, Katerina, thank you very much for the invitation. It's a great pleasure. It's a format I'm not familiar with. I'll do my best, but it's great to try new things.
Wonderful. That's great. And before we usually start to get into the science, we ask a few questions about how did you choose like science as your life path? Is that something you always wanted to do? Was there maybe a teacher, a class you took, or a book you read that kind of sparked your interest in,
Yes,
spending your
so
life?
for sure. I mean, it certainly wasn't my upbringing. I mean, no one from my family had been to university, uh, you know, i- to get a degree, let alone pursued a career in science. So it wasn't that. But as a child, I was fascinated with the underwater world. I think reading Jacques Cousteau's books and seeing those movies from the 60s. I grew up in the 70s, and those Jacques Cousteau's movies were still on TV and shown often in those days, and I became very interested in the underwater world. And then I learned to scuba dive in 1989. I was very young at the time, actually. It's quite young to learn to scuba dive. I think I was only 13 or so. And then I started to work in um, teaching scuba diving in Egypt, actually, in the Red Sea, which I'll talk about today. And then I met somebody who came to scuba dive at the organization I was working for. His name was Jeroen Kenter. He's Dutch, and he had actually just been in Miami, where I am based now, and was pursuing a career in marine geology and had been working offshore. And he told me the stories about that amazing work. And that inspired me then to go and do a bachelor's degree in marine biology, and then that's how I got into science. And so it's really, so the earliest memories I can remember, I wanted to, in those days, be a frogman, you'd call it. I suppose that became known as a scuba diver. So that's how I got into it.
Wow, that's really interesting. I love those movies and those stories too, and scuba diving. But
Yeah.
somehow, I went to neuroscience.
Yes.
So that's really interesting, that you went with your curiosity. I think that's always, I get the feedback from the audience and in general that it's something we all kind of are delighted about, that so many scientists that come here choose the path of curiosity. It's quite amazing to hear that. And is there maybe like a backstory to this projects? Was it easy to get funding? How did these papers come about? Like, yeah.
Well, that is an interesting story, and it really goes back actually to the very beginning. So I had lived in the Red Sea in the early 90s, teaching scuba diving, and then when I went to Amsterdam to do my master's and my PhD. In fact, even when I was doing my bachelor's degree, I was lucky enough to go back to the Red Sea and work there on projects. And I therefore also developed a history of work in the Red Sea. And this project that I will talk about today was done in collaboration with a wonderful organization called Ocean X, um, who have an incredible research ship. They're a philanthropic organization dedicated to marine sort of media and outreach and education, and also marine science. And I've been fortunate enough also to work along the Saudi Arabian coastline of the Red Sea in the past. It's a difficult place to work because Saudi was a sort of a closed country, at least up until recently. And there's a big development ongoing in Saudi Arabia called NEOM, where they're sort of developing their Red Sea coastline like Egypt had done, in the 2000s or so, 20 years earlier. And there was a joint expedition funded by NEOM and enabled by Ocean X. And because of my sort of long-term history in the Red Sea, I was invited to join it. And these are the discoveries that we made on the Ocean X vessel called Ocean Explorer, which if you should Google and have a look at, it's incredible. And we were using submarines, which are on the vessel and able to go down deep into the Red Sea in areas which are really had never been explored before. So that's the backstory to this.
Oh wow, that's fascinating. That's a really cool backstory. So I'm glad I asked. And yeah, now if you would like to guide us a little bit through your research, and yeah, as you said, please everyone feel free to ask questions. Either raise your hand or use the chat option. And yeah, the stage is yours, Sam. Thank you.
Okay, well, thank you, Catherine. I really appreciate it. Before we get into the science, I'd like to give a little bit of a background on the Red Sea because that will become relevant as I present the science. And it's a very fascinating part of the world. In fact, that whole Middle Eastern area, we call it the Fertile Crescent. And it's really considered to be the cradle of human civilization. And that crescent is really demarked by the Tigris and Euphrates rivers, which go down into the Persian Arabian Gulf, and then the Jordan and the Nile rivers, which are to the west side of the Red Sea. And it's in this part of the world that we see the first evidence for agriculture and irrigation. Writing seems to have been invented here, as were the wheel and glass and so on. So this part of the Middle East is really a very interesting area for humanity. And the Red Sea, which is, one of my loves, is relevant on human timescales as well, because the Red Sea is just incredibly, incredibly young. So geologically, the Red Sea starts to form only about 30 million years ago. That might seem like a long time ago, but in geological time, that's just an eye blink away. And you have tectonic movements. The Arabian plate is moving away from the African, literally tearing the Earth apart. And the basin that forms in that tear is what we call now the Red Sea. And it starts to form about 30 million years ago and gently widens, and really was not in its fully developed stage when the first human-like hominids were moving through this area. I mean, up to 4 million years ago, you'd have had early hominids migrating out of Africa, and they would have encountered the Red Sea and had to cross it, but it'd be very different to you see today. It would be much narrower, and particularly so in the south where these hominids were crossing, and in the north of the Red Sea where you have the Gulf of Aqaba and the Gulf of Suez, which leads up to the Suez Canal. They would have hardly have been open at all at that point. So the Nile, which runs parallel to the Red Sea, even disappeared around 2 million years ago and only appeared again about 1 million years ago. So, and then finally, our modern human ancestors, they would have made the final crossing of the Red Sea, moving out of Africa about 125,000 years ago. So the Red Sea has really sort of been evolving on human timescales. That's the point that I want to make. Now, critical to what I will talk about today is the concept that the Red Sea, because it has such a narrow link to the Indian Ocean, as there's tectonic movements in the area and sea level goes up and down with the ice ages, the Red Sea is occasionally restricted. That is, it's cut off from the Indian Ocean. And that happened about 15 million years ago. It became isolated, and all of the seawater that was in the Red Sea evaporated. In this sort of arid Middle East climate, water evaporates at about a meter per year, and so the Red Sea is a few thousand meters deep. So in a few thousand years, you evaporate all of the water in the Red Sea, and you leave behind salt deposits which are kilometers thick. And this might even have happened several times. And because of that, the underlying geology of the Red Sea, you have this huge, what we would call sequence of evaporites, or simply evaporated seawater leaving behind the salt. And that allows the seabed to move because the salt is ductile. It flows. And so you get a lot of very interesting geology in the Red Sea. And the reason that geologists are so enamored with the Red Sea is it's a great analog to the Atlantic as it opened up around 200 to 170 million years ago. The Atlantic would have basically looked like the Red Sea as that ocean basin started to form. And so we can study the Red Sea and understand the birth of oceans, great oceans like the Atlantic. And indeed, given time, given another 100 million years into the future, the Red Sea will open up to become a new great ocean on our planet. So I hope with that I've given a little example of why the Red Sea is so interesting, such an interesting place to work. And it's certainly special to me. As I say, I lived there in a tent on the coastline of southern Egypt in the early 90s. And I suppose subconsciously wanting to be a marine biologist, but there was something about that really arid desert-like coastline, which then grades into some of the richest coral reefs on Earth, which I found really evocative. And it was certainly a motivation in my own career, and why it was even more special to come back more recently and work in the great depths of the Red Sea with this fabulous organization, Ocean X. So we went to the Red Sea in 2020, late 2020, and I just got back actually a few weeks ago, and I've revisited again with Ocean X, using their incredible vessel, which is called the Ocean Explorer. It's nearly 90 meters long, carries about 75 people, and has incredible capabilities. There's two 3-person submarines, which are on the vessel, which have a diving depth down to 1,000 meters, so 1 kilometer, and then a remotely operated vehicle, a robot submarine, which can go much, much deeper, all the way down to 6 kilometers depth. So, adequate to get to the deepest points in the Red Sea. And beneath the vessel, in the hull, are incredible technologies for mapping the seabed. It's called a multi-beam, and it uses arcs of acoustic waves which are fired down to the seafloor, and they reflect and they come back to the vessel, and it builds up a 3D picture of the seabed. And a typical day on this vessel starts actually at night. So the scientists go to bed when we've finished processing our samples from the day prior, maybe around 11 o'clock. And the vessel at that point starts to survey the ocean floor using this multi-beam mapping technology. And all night the vessel is surveying on the area that we've designated. And then as a ship-going scientist, we wake up early, around 4:30 in the morning, maybe a quick cup of coffee, and then we go down to mission control, which is sort of the beating heart of the vessel, and we start to review the map which has been collected in the night before. So we huddle around huge computer screens, and we're looking at a 3-dimensional map of the deep ocean. And in certainly the case with the Red Sea, these are really explored areas, so you are often the first person to see what the seabed looks like. Then we make a plan for the day, and we pick spots on that map where they're going to deploy the assets from the ship. That would be the ROV, the robot submarine, and the submersibles. And we make a plan for those dives. Then it's a very quick breakfast. And then down into the sub hangar where the submarines are stored. And you start to get into the submarine. You're still absolutely inside a great hangar inside the vessel, and you close the hatch on the submarine, and you start to go through the safety and pressure checks, and all the while you can feel this huge ship maneuvering itself into position above the dive site, which is 1,000 meters below the vessel at that point. And then once the ship is in position, a huge hangar door opens, and the submarines are rolled out into the sunlight. It might be the first time you've seen sunlight that day, and a huge gantry comes down, picks up the submarine with you inside, and over the stern of the vessel you go, and you're dropped down into the water and released. And there's a quick check around the surface, and then you start the descent in the submarine, which is very exciting. It can take up to 2 hours to get down to the seafloor. And then gradually, as you go down, of course, the light disappears and you switch on the lights in the submarine, and you work your way down to the seabed, always in pairs. So it's two submarines going at the same time. So if one gets into difficulty, the other one can mount a rescue. So we go down to the seafloor. And typically in the submarine, we have on this cruise at least, we had a geologist like myself, and a marine biologist who might be studying deep sea corals or something, deep sea fish or something like that. I mean, there's actually, I'll just interject there, there's no real difference between a marine biologist and a geologist, because all of Earth's history is really played out in the ocean. So a geologist, I think, is just a marine biologist through time. So we have a lot in common. And we go down to the seabed and we start the work. And the project I want to talk about today, really comes from one day's dive, which was done in the Straits of Tiran. And if you look at any of those papers that Katerina has uploaded, you'll see maps in them with where the Straits of Tiran are. They separate the Gulf of Aqaba from the northern Red Sea. It's a very busy sort of international trade route. It's a shipping channel through there. Very difficult place actually to launch submarines because there's so many ships going past. And we went right down to 1,000 meters in an area we call the Tiran Deep. And I was looking at the geology and the tectonics in that area. And we were working our way up a precipitous underwater cliff, more than 1,000 meters high. And then we were just coming up to around 100 meters water depth. And at that point, I was sort of handing over the keys to the dive to the marine biologist, a fellow from Italy, Giovanni Chiamenti, who's an expert on deep sea corals. And he was starting his work, and we were starting to collect corals and photograph them and so. And I had opened my box of sandwiches, was starting to relax a little bit more and take in the scenery. And we were up on this terrace at about 100 meters water depth, as I say, and the submarine was driving forward, and we came across a cliff face, an escarpment, which none of us had anticipated that we would encounter. It was about sort of 5 to 10 meters high, and what you could see was that the seafloor had been broken catastrophically. There'd been a huge sort of force which had gone on in this area and broken the seabed. And that was a totally unexpected discovery, as the most in science are. I think the best discoveries are unexpected, and we started to analyze this escarpment that we had encountered. We were counting the corals on it because we know how quickly corals grow, and it was very evident from the beginning that this was quite young. It only, based on the corals, I would say less than a few hundred years at most, this incredible event had happened on the seabed. And we also took samples from the rock which constituted this scarp, and then we were carbon dating them later in the lab to see, also how old it was. And I don't know, go into the details, but we came to the conclusion this was about 500 years old. The seabed here in the Straits of Tehran had broken catastrophically. And we're interested in this because if you break the seafloor in this way, you can generate tsunami waves. This is one way of generating tsunami, is by sort of breaking the seafloor very quickly and very, to a large extent. And in the beginning, we thought that this was a fault, a tectonic fault that had ruptured, but there were several lines of evidence that pointed to that this was not the case. And we came to a second hypothesis, which was that actually this was an underwater landslide which had started, but then stopped after a few seconds. It had got hung up for an unknown reason at that point. So the seafloor had started to slide into the abyss, but got stuck. At that point, recognizing that an event like this could create a tsunami wave 500 years ago, I started to chase that scientific idea, and I teamed up with a guy who I'd never met at the time, but a fabulous scientist called Steve Ward. He's at the UC Santa Cruz in the seismology lab there, who is a tsunami modeler. And we took all of the measurements I had made from the submersible and the multi-beam data from the ship, and then started to make a simulation of the tsunami wave which would be created by such an event 500 years ago. And we went through that process, and one of the papers that Katerina uploaded is about this. And what we realized was that if you move the seabed in this way, you create a really large wave, and it would have hit the Sinai Peninsula of Egypt with a height of about 10 meters. I mean, anything over 2 meters is considered a major tsunami. The one which caused the meltdown of that reactor in Japan, by contrast, was about 4 meters high, and you'll remember that the footage of that. And this tsunami was probably about 10 meters high. But it was 500 years ago, and we asked the question, of course, had anyone, recorded this event in the Red Sea in the historical record? Well, if you go to the historical record, 500 years ago, this area of the Middle East was ruled under the Ottoman Empire, and the Ottomans, alongside making very comfy couches, of course, they also kept fastidious records of earthquakes and other natural disasters in their territory. But this event is not registered in the Ottoman records, actually. And that was confusing. And then we started to look at the Ottoman maps, and even maps which had been made up until a few hundred years ago. And what we realize is this part of the Gulf of Aqaba where we think the tsunami occurred was basically uninhabited at that time. It wasn't even up until the 1970s that local fishermen started to fish in this area and have an occasional base there. So, it wasn't a surprise at that point that the tsunami had been missed in the historical record, and particularly so because our simulation showed that the wave was really projected up the Gulf of Aqaba, which was largely uninhabited at the time, and not down into the Red Sea where there were Ottoman settlements. And so it was just the geometry of the Tiran Straits which prevented the wave going into that direction. So that was interesting, and at that point we started to think about whether the wave had been captured not in the historical record but in the geological. So we went then further to the north in the Gulf of Aqaba and started to make dives into much deeper water, way beyond the diving depth of the submarines, and now using the robot submarine, which went all the way down to the deepest depths in the Gulf of Aqaba. We picked an area which was called the Aragonese Deep. It's about 2,500 meters deep, so more than a mile. And we were looking at the multi-beam maps we had made from the ship in this area, and I had a hunch that this might be an area where we get brine pools starting to form on the seafloor. And that my hunch for that came from the tectonics in the area. And you'll remember back at the beginning of the presentation, I gave this notion that there was thick salt deposits which were distributed beneath the seabed from the early evolution of the Red Sea. And these faults, I had the hunch that seawater might be mobilizing down through the fault network and dissolving these sub seabed salt deposits, and then that waters would be coming back up onto the seafloor as a very dense brine. And if that can happen, you form what is called a brine pool or a brine lake, and they're absolutely fascinating areas. So if you encounter a brine pool, it looks like a sort of a pond, as you would encounter on land, with a shoreline and then the water in the middle of it. But here you're a mile deep in the ocean, and the brine is so dense that it fills in depressions on the seafloor and forms these underwater lakes. I had a hunch. So we positioned the vessel above the Aragonese Deep, and we launched the remotely operated vehicle, the ROV, down to it was down to nearly 2.5 kilometers. Also took several hours to get down there. And then we started to drive the ROV along the seabed. I mean, it creeps along just 1 or 2 knots, sort of like a walking pace, really. And we made our way across the seafloor. And of course, I was hoping we would drop down and immediately see a brine pool. Well, that wasn't the case. It was just a barren desert, just a muddy, flat seabed, perhaps about as boring as you could ever, think up. And gradually we worked our way across this boring, muddy seafloor, hour after hour after hour. What I'm acutely aware of is all of the footage from the ROV is being beamed all around the ship. It goes to the cooks in the kitchen and the captain on the bridge and the engineers in the engine room, all looking at the footage coming from the seafloor and expecting something wildly exciting to happen. And hour after hour went past with nothing but this barren, muddy seafloor. And because the end of the dive has a set time that we need to get the ROV back onto the deck, I knew I could see sort of the clock ticking down. And we got to the point where there was literally just 15 minutes left. We'd been doing this for 9 hours. I was absolutely crestfallen at this stage that we hadn't found the brine pool. And I was ready to give up, but I said, no, okay, we've got 15 minutes left. Let's just go to the bitter end. Well, with 5 minutes to go into the cameras of the ROV, which were being beamed up to where we were sat in mission control, we saw the coastline of the brine pool. I mean, it absolutely, fantastic. And, other people in the ship had recognized it. And within a few minutes, we probably had 40 or 50 people in mission control, gathering around the screens. And as the ROV moved out over the brine surface, the thrusters from the vehicle, they put a sort of wave into the brine, and you could see it propagate in slow motion across the pool, which was about 10,000 square meters. It was, I suppose, even a brine pool doesn't do it justice. It was more like a brine lake. I mean, incredible. And the reason that we were so excited by this discovery is really twofold. And the first is that the microbes which live in the pool and beneath it are some of the most extreme examples of life on planet Earth. They live, of course, at great pressures at the bottom of the ocean, but also there's zero oxygen in the brine. It's completely anoxic, so it's a very challenging environment. It has a very curious chemistry. Of course, it's incredibly saline, yet still life exists there. And studying these microbes has led in other work, not by me, but by people who study these sort of extreme organisms, to compounds which seem to have anti-cancer properties. So there's, medical advances made from this extreme life. But what really interests me is that it seems to be, from our understanding, a good analog to the first life on Earth, which we believe the first life on our planet was in these extreme hydrothermal systems in the deep ocean just shy of 4 billion years ago. And understanding this extreme life might also guide our search for extraterrestrial life on other planets, which we might call ocean worlds, which have similar oceans with hydrothermal systems active beneath them. So we might learn about the search for extraterrestrial life as well. And as soon as we saw this brine pool, we saw these extremophile microbes, as we call them, staining the sediment all the way around it. So we really found, what we were looking for here. And it wasn't just the microbes. I mean, there seemed to be many animals as well. There was fish and shrimp and eels, which were clearly using the brine as a feeding strategy. Because there's no oxygen in it, any animal, unlucky animal, which makes its way into the brine is immediately stunned or killed, and these animals were then scooping them out and feeding upon them. So they were essentially using the brine pool as a trap. So that was a very interesting thing to observe. Of course, then having found the brine pool, we could then dedicate some more days to researching it in 2020. And also, I just got back from another expedition where we had a day we managed to visit it just a few weeks ago. Every time it's a privilege. Now, to bring the story back to the tsunami, the incredible thing about the brine pool is that it has no oxygen in it. And that means that any sediments which are laid down on the bed of the brine pool aren't chewed up, or what we would say scientifically bioturbated, by all the animals that usually make their home in the seabed. I'm thinking about the shrimps and the clams and the burrowing worms and all the things which churn up the seafloor are explicitly excluded from the brine pool because it's utterly devoid of oxygen. So to capitalize on that, we took some cores. That is, we used the ROV to push pipes down through the brine to the bed beneath it, to the bed of the brine pool, and then push those pipes down deeply into the seabed, and then pull them out again and bring them back up to the surface. And contained within the pipes then is an exquisite record of the sediments which have been laid down into the brine pool. And we use carbon dating and uranium thorium dating to work out the age of the sediments. And the record that we managed to retrieve in that case went back to about 1,300 years ago. And when first of all, we scan the cores in a CT scanner, just like you would go to if you'd broken a leg in a hospital, to look inside the core. And then once we think we understand it, we cut it open and split it in half, and then photograph it and scan it, and do all sort of scanning also on the minerals and the chemicals which are in the core. And what we saw really sort of exceeded our expectations, and that is that there was two flavors or motifs to the layering of the sediments. So the first was very fine millimeter scale layering, and from work which had been done offshore Israel, what we understand is that each millimeter there is a flood event. Where of course, the Middle East is very arid, it doesn't rain very much, but occasionally it does rain, and very heavily, and you get a lot of rivers which are inactive for the most part, but they become activated. These are called wadis in the Arabic language, and that puts a lot of rainwater down into the Red Sea, the Gulf of Aqaba, and we see the record for that in the brine pool. And our preliminary analysis, but we're still working on it, is that you have these very major flood events about once every 25 years in this part of the world. The second thing that we noticed in the cores were thick layers of sand, and because of the size of the grains and their angularity, we could see these were coastal sands from the coastal plains surrounding the Gulf of Aqaba, and two cores have been blown into the sea by wind. And what we think these layers are deposited down by major earthquakes in the region, which literally sort of shake the beach sand into the ocean, and then it gets transported down more than a mile to settle in the brine pool, but also major tsunami, which have occurred in prehistory in this area. And those tsunami waves, they ride up onto the coastal plain, and as they retreat back into the ocean, they bring with them a lot of detritus, including these thick terrestrial sand deposits, which are then exquisitely preserved in the brine pool. And using the carbon dating, we believe that in the last 1300 years, that there's major tsunami about once per 100 years, about once per century. And as I said at the beginning of the little talk I'm giving here, that we think that we found evidence for a major tsunami 500 years ago, a little bit further to the south. Indeed, here we find a thick sand deposit, which we date to 500 years old. So even though that the Ottomans, they didn't capture this event in their records, we find the geologic evidence in this incredible brine pool environment that we've discovered. And really now to sort of close the presentation, I want to answer the so what, which is why do we care about any of this? Well, I think the brine pool is fascinating in its own right because it represents life as its absolute most extreme on the planet. But the so what for the flood events, and in particular the tsunami, is that although the Gulf of Aqaba has been uninhabited until very recently, that's not the case anymore. And it's urbanizing at a rate, which is really extreme to anywhere on Earth. You have great developments on the Egyptian side of the Gulf of Aqaba, the dive resorts of Sharm el Sheikh and Dahab, and so on and so forth, which are home to tens of thousands of people and millions of visitors each year. But now also on the Saudi Arabian side, you have these huge, which are called giga projects, which are starting to be built, the cities of the future, as they've been termed, which come right up to the coastline. And then, of course, you have Jordan and Israel up the end of the Gulf of Aqaba. And if there's a tsunami threat in this region, even if it occurs only once per 100 years, of course, this is something which needs to be understood. It needs to be known about, and it needs to be monitored. And certainly, I'm not advocating that you can't develop the coastline here. I mean, people live in proximity to major geohazards very happily. You could think about Los Angeles on the San Andreas Fault, for example, or even in Portugal. I know, Catarina, where you hail from, you have great earthquakes as well. Lisbon suffered a massive earthquake hundreds of years ago, but still it's a thriving city. The point is that you have to understand these threats, and that's why I think that this research is important, because it informs, risks that people may face in the future living in the area, and with knowledge comes good decision making. And I hope that the research that I'm doing contribute to that. So really, in closing, the Red Sea is a very special place for humanity. It's a special place to me. I lived there in the early 90s as a very young lad, and really that's where I developed my love of marine biology and the ocean. And it's this harsh mountainous desert landscape, which is really what I fell in love with, and then the deep blue sea in front of it. I mean, that landscape speaks to the underlying geological processes, and I hope that these discoveries that we've made, such as the brine pool and the underwater landslide, all in the Gulf of Aqaba, start to educate us how young oceans are formed and how we might expect to live in these boisterous, tectonically active areas on the planet. All right, then. Well, I'm happy to answer any questions, and very grateful for your attention.
Thank you so much, Sam, for bringing us along your deep sea adventures. This was such an amazing talk that really, I don't know, took us along a little bit, and it's so fascinating. And I don't know if anyone was ever in these submarines that go into the deep sea. I was in one when they displayed it at the Oceanographic Institute. I'm not sure if I could do it. But it's really to how many hours do you spend? And yeah, I think it's about 8 hours or something.
Yes, yeah. I mean, it's long. So yes, the longest dives are 8 or sometimes even 9 hours. I mean, it's quite cramped. There's a pilot of the submarine and two seats. So typically two scientists. So and you're sitting very close together. Perhaps imagine sitting in a cinema, but a little bit closer than that. And you're inside a acrylic dome. So certainly you don't feel claustrophobic because you can see almost 360 degrees around. But yes, I mean you have to sort of train yourself for not being able to go to the bathroom, if I can put it in blunt terms. For sort of 8 or 9 hours. But you get the hang of that, and if you're doing it every day, you sort of moderate how much you drink, not too little, so you become dehydrated, but you sort of moderate that, and it's amazing, yes. And the time flies by because it's such a privilege to be in the deep sea and to see it. And yeah, I mean, the day is gone before you know what's going on. You descend from the surface in the early morning, and you come up in the evening, and the sun's going down, and you can't believe that a day's gone by.
Wow, that must be amazing. So, yeah, and thanks for the sharing this wonderful work. And I'm so glad you stayed those 5 minutes longer.
Yes, yeah, it just goes to show. I think if you're doing this every day and the cruise can be for a month or more, you can get a bit blasé. But every moment you have to explore the deep sea, there's a discovery just around the corner, and so you have to take full advantage of that privilege. And of course, it's very expensive. The ship is incredibly expensive to operate. There's a crew of 50 or so people who are working, hard every minute of the day to allow the ship to operate and to give you this opportunity. And so, yeah, I mean, you have to seize the moment.
Wow, incredible. And how is it with getting like permission to go on these explorations? Is it nowadays more complicated than it used to be
Yeah, it's
with all the
it's very complicated. And but OceanX, this wonderful organization who operates their research vessel, of course, they have experience doing this because they work all over the world. But suffice to say, the permissions and the permits from the Navy and other governmental organizations in whichever country you're working also take years to put into place. And occasionally you're involved in expeditions which straddle the boundary of multiple countries, and all of that has to be coordinated. But suffice to say, you can pass through these areas in international waters. That's within the law, but you certainly can't start mapping the seafloor or launching submarines without a massive effort. And indeed, normally on the vessel you have representatives from the country, perhaps from the Navy and the Department of Interior or so, who are checking what you're doing and making sure that you stay within the bounds of your permit. So we have to be very careful of that.
Yeah, I can imagine. And so I just ask a question, and then everyone else I'll give time to ask questions. So the samples you brought back, what was the biggest, or biggest is kind of stupid, but what does the from the samples that you brought back, what do you think will it tell us also about the future? Can we maybe learn? You touched a little bit on it, about what we can learn from the earthquakes and the
Yes.
different tsunamis. So, but is there maybe something climate related that you
Yes, there absolutely is actually, and that is so. In terms of climate change, it was always predicted that the Middle East uh, will is one of the areas where climate change is going to be felt earliest and most acute. And indeed, that's that's the case. There's been a great increase of aridity, drop in rainfall in the Middle East, and an increase in temperature, as the climate models predicted. To predict the future through modeling the climate, we have to understand the past. I mean, this is sort of how these models work, is that you first make sure that you can correctly predict the past, and then you run the model into the future to give you some confidence that it's correct. And understanding the climate in the Middle East in the past, in order to predict the future, has been tricky because there aren't great records. These cores, which are, totally undisturbed in the brine pool because there's no oxygen and no animals that live, churn up the seafloor, they record rainfall events, with annual fidelity, and that's a unique record. But we also could understand the direction that the winds were blowing over the last 1,000 years, because the wind blows dust into the ocean and it settles down to the seafloor. And you can look at the mineralogy of that dust and see from where it came, which part of Africa the dust blew from. And then you can build up an idea of which way the prevailing winds were blowing at different points in Earth's history. And so we can do those reconstructions and calibrate the climate records for the past, and then that greatly enhances our ability to predict climate into the future. So there very much is a climate aspect of that, and that was a very astute question, actually.
Thank you. Yeah, that's really interesting. Yeah, so please flash your microphones or write in the chat if you have questions. I saw Joyce unmiked, and Kyle and Kirko joined us here on the stage. Please go ahead, just in PTR order, maybe. Thank you. I guess Kirko is away, so Joyce, please go ahead. Thank you.
Okay. Well, I missed quite a bit of it, but I was interested from the microbiological point of view. Is there anything that you found or your collaborators found about the microbial communities? I'm particularly interested in extremophiles and how, for instance, they found new species of microbes or variants of microbes that can feed on the cleaning solutions that NASA uses in their clean rooms. Mm-hmm. So just to give an idea of how extreme and how microbes are so ubiquitous in places we had no idea they could live.
Right. Okay. So I mean, I'll add a sort of qualifier to that, is that, I'm a geologist and not a microbiologist, but we are working with microbiologists, always looking for more collaborators. I mean, Joyce, if you're interested in such things, please do, send me an email. It could be great to, work with you on it, because we do have a lot of samples. But one thing that we're finding with the sort of geological aspect here is that we know that in deep geological time, microbes are responsible for the deposition of a lot of the rocks which record Earth's history. And many of the great reef systems hundreds of millions of years ago, we now understand were essentially actually built by microbes, which can precipitate limestone, calcium carbonate, and they're real ecosystem architects, building vast edifices, huge reef systems, which are now sort of preserved. If you went to New Mexico, for example, the great mountain ranges there are microbial reefs. What we see around the brine pool are the microbes which seem to have the capability to undertake these sort of actions. And what we originally thought is, when we see these deposits in the geological record, we think they speak to shallow waters, sort of snorkeling depth waters, or waters you'd wade across. But what we think we're recognizing now is a lot of this microbial activity, which precipitates limestone, might have actually been happening in the much deeper sea. As I say, we're more than a mile down in this case. So that's that. But I am looking for collaborators, who are experts on microbes and sequencing them. And we've done a little bit of sequencing, but it's certainly not our prime expertise. So, if you'd like to get involved, please reach out to me.
Well, thanks. Very interesting.
So I was super curious. When it comes to like, uh, I guess like microbes' ability to survive, and this is something I don't know. Because I think you said something about like you tend to find like some of these like brine pools where like there's more like tectonic activity. So I was kind of curious if like like if there's heat, I guess, that like ends up uh being brought into like the system of the brine pool that
Yeah,
helps these things like stabilize. So like the question is like if we were looking for like life on other planets, would the planets the potential for tectonic activity be like one of the potential like limiting factors
yeah,
for if we find like you know what I'm saying?
yeah. I know exactly what you're saying, Kirko, and it's a great question. And um, our guess, and of course this is all a guess, that tectonics, plate tectonics, is a or might be a precondition for the development of life on a planet. And the reason for that is that otherwise, if you don't have plate tectonics, through gravity, things work their way. And let's take our hypothetical extraterrestrial planet, which does have an ocean. Doesn't have to be liquid water, but it's liquid something. The landscape starts to erode, and eventually, a lot of material ends up in the deep sea. Um, and it stays there if you don't have plate tectonics, is the problem. And you start to sort of denude the surface of that planet from key elements and minerals, which might be key to the foundation of life. If you have plate tectonics, it's only then you have a means of getting that stuff back up, to the surface of the planet. And the way it works, of course, is that the tectonic plates move and they subduct down into the core of the planet where they're melted, and then they're remobilized and they come out of volcanoes as lava and gases. And you have what we call the rock cycle, which goes, for a given atom to make that circuit, it might take 100 million years, but it's an effective way of recycling material. And if you don't have plate tectonics, you don't have that. But as we see with the brine pools here, and other deep sea areas like the mid-Atlantic spreading ridge, and so on and so forth, and it's those sort of areas that we think that life appears on this planet, is by mixing chemicals with different gradients of heat, like sort of hydrothermal vents and hydrothermal circulation offer that opportunity. That seems to be a very fertile area for the chemistry experiments from which life, miraculously seems to spring from. So, plate tectonics is important for this recycling of material on long time scales, but it also develops the niches or niches, you might say. I say niches, potato, potato. It develops the niches which seem to be a good place to do life experiments.
Cool, thanks.
Yeah, thank you so much. I think Parth had a question.
More than a question, I just wanted to congratulate Sam for the paper. It's I'll put it in my list of to read papers for today. Thank you for this room. Congratulations, Sam.
Well, thank you for your interest.
Yeah. So I was quite intrigued because we know that deep brine pools have immense significance for looking for potential life on places like Mars, where I think they have indeed found deep brines subsurface. Correct me if I'm wrong. Therefore, they have a lot of implications for looking for potential life on Mars. Number one. Number two, even otherwise, even if you were to take that factor away, the implications for life on Mars, even if you were to discount that, the very fact that you have made this discovery brings up a lot of questions. For example, what are their survival mechanisms? Do they survive the same way extreme halophiles survive on salt pans, like the ones in Salt Lake City or the ones found near Owens Lake in California? We know that aerobic extremophilic halophiles, they use bacteriorhodopsin and other pigments to harness energy. So what is the source of energy for them in these deep brine pools? Because they're subsurface, they don't have access to light. So what is their source of energy? And what is everything about them would be fascinating if you had to do find out their growth rate or their cell division, right from cell physiology to their metabolism, metabolic pathways to their genomics. So I would like to. My PhD was on halophiles, by the way. I worked on. Yeah, I got my PhD in India. I worked on extreme halophiles from the salt pans on the west coast of India, and we also isolated samples from deep sea, not deep sea. I wouldn't call them deep sea. 200 meters is not deep sea. From the continental shelf of India to look for extreme halophiles and also their ability to degrade hydrocarbons. That was my PhD thesis.
Yeah.
We found many of them were able to tolerate a broad range. They were kind of halo tolerant from 5%, 3% salt all the way up to 25% salt. These were organisms that were living in not so extreme halophilic conditions like subsurface. They were found in at the depth of 200 meters, benthic continental shelf. I participated in a few research cruises for the Oil and Natural Gas Commission's environmental monitoring research teams. That is when we collected the samples, and that became part of my PhD work.
Yeah.
And they not only were they able to tolerate a broad range of salt, they are also able to degrade hydrocarbons. That was my
So I mean, there's a few things to unpack there, and it's fascinating work that you've done there, Path. I mean, in terms of in our solar system, analogs would be icy moons like Europa, Titan, and Ganymede, and so, which we think, certainly have ice water and maybe liquid water beneath, and are good candidates also for the tectonics, which might set up the hydrothermal systems um, um, to produce a sort of an analogous environment to we're seeing here in the deep sea, and of course also that hydrothermal system necessary to melt the ice possible. Even Pluto is thought maybe to have sub-ice oceans. In terms of the metabolisms, just as you say, yes, they have a diverse sort of suite of metabolisms. They are metabolizing sulfur, manganese might also be relevant in there, and so on and so forth. So it's not my expertise. I'm not a expert on the biology of microbes. So we are doing some genetic sequencing and trying to disentangle their metabolisms. But certainly, yes, they're very curious in the way that these very simple organisms have modified themselves to live in such extreme conditions. And I mean, I think halophiles like you studied, or extremophiles more generally, there's a lot to learn from life at its most extreme. One thing which was very interesting is the temperature of these pools, because of course we didn't know that as we discovered them, but at a certain point we had to start to lower very expensive equipment into the pools to take samples, and it's really a leap of faith. And it turned out that these are not that hot. They're a few degrees warmer than ambient, but there's cases of brine pools being 50, 60 degrees Celsius warmer than ambient. These weren't that hot, but we didn't know that at the time of the discovery, and really had to start to lower probes into them with the risk of losing them. But it was all okay. And because it's not that hot, it probably intimates that the hydrothermal system, which is driving the circulation, is quite far removed from the brine pools in the subsurface. But it's still hydrothermal. It is the engine which is making the brine pools form. I hope that answers the question.
Yeah. Great point, Sam. I really appreciate that. I also thought it's important for me to share this. Geologist Barbara Sherwood Lawler of the University of Toronto, in 2009, she and her team discovered a discovered 1.6 billion year old water in a Canadian mine 2.4 kilometers below the Earth.
Yes. Yes.
Likewise, the recently deceased colleague, it's a life comes of full circle. It's
Yes.
one of the sadder moments in recent times. Dr. Professor Tullis Onstad from Princeton, he
Yeah.
recently passed. I was it was very heartbreaking because years ago, when I was looking for a postdoc, he was one of the few people who responded to my postdoc requests. And then I came to know recently that he passed. So it was he has done significant work in subsurface microbiology. In
Yes.
fact, his work, along with the others, created this what is that? Deep carbon? What is it called? There's a project. It's a subsurface looking for life in subsurface conditions, completely cut off from the rest of. They're completely isolated from the rest of the environment. I do
Yeah.
not word for it.
Yes.
Deep carbon observatory. I think that's the word, if I'm not
Yes.
mistaken.
Yeah.
Yeah.
I mean, I'm certainly aware of the work, and the salient message here is that the deeper you look, you keep finding life, and I suppose the learning for that again is if you're looking for life on other planets, and Mars might be an example. Just because the surface is devoid of life, it doesn't mean that the deep subsurface is. And that work that you were mentioning coming out of Princeton and so has shown that these deep biospheres can be cut off from the surface for tens or even perhaps hundreds of millions of years. So, life can go extinct on the surface, but, still persist for geologic time deep below the surface of a planet.
Yeah. And I mean, we we have hardly covered 25% of what we know on planet Earth. So that's the reason why the kind of findings that you have come up with this particular paper, it's all very significant. I'm all 100% for discovering more of life on planet Earth itself, because every time we find something, we keep pushing the limits of life. I'll just give two examples. When Deinococcus radiodurans, which is a name of a microorganism for those who are non-microbiologists, when it was found to tolerate 5,000 grays of radiation. So
Yes.
a grays of radiation, so I'll have to give a little bit of background on that. 10 or 25 grays of radiation is more than enough to kill a human being, long exposure. But these organisms, microorganisms, can survive 5,000 grays of radiation. It was thought it was incredible. But then now we have Kiniococcus species that can survive 10,000 grays of radiation. And then 5 years ago, uh, an archaeal isolate was found in the Guaymas Basin in Mexico. This can tolerate, believe it or not, 20,000 grays of radiation.
Yes,
That is
incredible.
it's incredible. That level of radiation should be obliterating the entire genome. Yet, this organism is managing to not only survive, not only tolerate but also survive. So, and I've not kept touch with the kind of work they are doing on organisms like this. But the overarching point I'm trying to make is we keep finding life that keeps telling us how little we know and how much of life that we are yet to discover. Their ability to survive and redefine the limits of life. So thank you again, Sam.
Perfect. Perfect. Well, look, it's exciting work you're doing as well, Path. So, good to have spoken to you.
Absolutely, I'd be more than happy to share those papers with you. I think Katrina sent me your email. I'll try to be in touch with you, Sam.
Perfect. Look forward to it. Yes.
Robert, you joined the stage. Robert was saying, how amazing this work is. Welcome, Robert.
Hey, I'm just here nerding out as a not officially a geographer, but I studied it. But love what you all are talking about. Keep going, and I'm just here to cheer you on.
Well, Robert, I appreciate it. Thank you so much.
Kyle, I saw you unmute. How are you?
Yeah, yeah. Sam, amazing presentation. I almost got immersed in the story like I was sitting there having a sandwich with you.
Very good.
So it was great. I actually, Parth kind of touched on something, the importance of UV light for the origins of life. And so there's an article that I kind of posted. It was from Nature magazine, and it's talked about the water paradox and the origins of life. And it's because several studies suggest that basic chemicals of life require ultraviolet radiation from sunlight to form, um, and that the watery environment had to become highly concentrated or even dry out completely at times. So this just immediately, when I saw the title of the room, I thought of Bruce Damer's work with the volcanic hot springs and the origin of life. And the idea is that these hot springs kind of were like brine pools, and they would basically dry out and basically fill back up. And throughout that constant cycle of drying and filling, it seems to have created some sort of polymer um, that was operating like a grid, being dried out and um, filled back up with water and dried out to create another layer over another layer over another
Hmm.
layer over another layer, and then this leading to like the origin of life eventually. So I was just wondering if you looked into this, and then also something else that I thought of was Lee Cronin is doing a lot of work with computer modeling and chemistry, that he might even be able to do and model out some stuff for you and your team as it relates to brine pools, because that's something also that Bruce Damer has done to kind of show how this could happen on different planets, such as Mars as well, and has utilized metaphor and computer programming as well in his research. So I was just wondering, have you talked to anybody about the idea of these brine pools and their location, whether or not it's near volcanic activity for heat and sunlight, or is it at the bottom of the ocean, which would then lead us to kind of this paradox that I was referring to from that Nature magazine?
Yeah, I mean, so very good suggestions, and I'm grateful for them. I mean, yes, this is at the bottom of the ocean. We're a mile beneath the ocean surface, a bit more than a mile actually, so it's very deep. Certainly, I'm familiar with these arguments, about where life on Earth initiates, and you've there's sort of two competing views on this. The first, as you say, was sort of tidal pools, perhaps with hydrothermal activity involved. That was originally proposed by Harold Urey, back in the 50s, the primordial soup hypothesis, it became known as. And then it sort of fell out of favor, but is coming back in again. Um, I mean, it's curious when life appears on the planet um, with regard to the formation of Earth's core and Earth's magnetic field. Like, certainly, it seems that complex life appears about only 500 million years ago, 500 million years ago, at the time that Earth's core has finished maturing, and you start to get the magnetic fields, the geodynamo fully developed, and then protection through the geodynamo from high energy particles streaming off the sun, what we call the solar wind. And of course, the manifestation of the interaction with that solar wind with the Earth's magnetic field is the northern lights, the aurora borealis. And there's a hypothesis that it wasn't until that point where the Earth was protected from these high energy particles that complex life could appear on its surface, and before that, simple life as it was even then restricted to being underwater, because that provided a blanket, which prevented damage from these high energy particles. So I don't have an answer for you, and I don't think your question was in that direction. I mean, because this is something still under debate, but to my mind, I would still push as the first life on this planet to be in the deep ocean. I think, and the reason for that is the game of numbers. Is that deep sea spreading ridges where tectonic plates are moving apart? I mean, sort of what's happening here in the Red Sea, indeed, and the Mid-Atlantic ridge. is a great example, are thousands of miles long. But they have incredible gradients of temperature and chemistry, even on sort of millimeter scale, let alone meter scale. And if you run those chemistry experiments for hundreds of millions of years, and just one further point there is that the hydrothermal fluids which come out of the vents there, they have, sort of very essential minerals and metals, and so dissolve within them. And clays. You get a lot of clay which comes out of these systems as well, which we believe serves as a scaffolding for more complex molecules. So if you run these experiments, every second of every day for hundreds of millions of years with different gradients of temperature and clay and minerals, so on and so forth, that seems a logical place to create life because of the law of large numbers. At a certain point, you've done so many experiments, you get it right. But I totally hear what you're saying about the shallow and the need for ultraviolet light as well. I mean, in the end, we will probably never know the answer to this, beyond the fact that life did appear on this planet, around 4 billion years ago, or a little bit short of that. So, I think there's a great discussion to be had.
Well, yeah, you hit the nail on the head. It feels like we're in a massive paradigm shift. Just they're just sending. They're just like there's this data that came back from James Webb that has got people kind of a little flustered and maybe crunching numbers. And there's been murmurs about questioning the Big Bang Theory as a result, and also. NASA's testing out some cosmological theories right now. So it is interesting that with AI, I think or machine learning, I think we are finding ourselves in a little paradigm shift here. And so you elegantly and well articulately spoke what I was referring to, and thank you so much for your time and energy, Sam.
Well, thank
been
you.
Amazing.
Thanks for your interest. It's a great pleasure.
Yeah, I wanted to take the time to ask a couple of questions that were in the chat asked. So Alexander, he asked the tectonic setting of Southeast Asia and the collision zone formed between the Eurasian and Indo-Australian plates. Are we anticipating any similarity would happen in the Red Sea? And he also asked if seismic activities in the Red Sea, if they are as significant as in the Pacific Ring of Fire.
Okay, well, super question. So I'll answer the second one first, and that is the seismic activity in the Red Sea. Yes, it is. It's a very seismically active area, on a scale of that you do have in on the edge of the Pacific. Different reason, of course. The Red Sea is extensional; it's splitting apart, whereas the Pacific Rim of Fire is convergent. That is, you have an ocean plate subducting under the continental crust there, and forming volcanoes and also earthquakes. So different mechanisms, but similar magnitudes, it seems. In terms of seeing such, similar setups in Southeast Asia, I think the key here is, yes, you have, sort of ample tectonics, and you have this subsea bed salt, which can be mobilized to form the brine. And that isn't unique to the Red Sea, even though we do find the most brine pools in the Red Sea. You also have cases in the Mediterranean and the Gulf of Mexico. And I'm sure there's other places around the world where such discoveries will be made in the future, because it's not a unique geological setting. And just as I say, such a setting would have been very common, also when the Atlantic was forming, albeit 170 million years ago or thereabouts. So yes, I think there is a chance, to make similar discoveries elsewhere. It's a question of looking in the deep sea, and that's a very expensive and difficult thing to do, which brings full circle, why this sort of research is so important, and organizations like Ocean X that facilitate it are so valuable.
Thank you. And I think Robert had the last, because I think you have to leave now soon. Robert had the last very cool question maybe to ask.
Okay.
Oh, well, there's some of us, and not like a tourist, but there's some of us that pop in places just to observe. Not just yourself, but even Ocean X.
Uh-huh.
If there is someone of interest that would be interested in just observing, not getting in the way, is that possible?
Well, that's a good question. I mean, and I think different organizations and federal agencies which have vessels which go to such places. They all have different policies, but certainly I know some organizations, including actually the U.S. With NOAA, the National Ocean and Atmospheric.
Very familiar with NOAA.
You're very familiar with NOAA. I mean, they have opportunities for artists to join science programs, to try to marry art and science together. And I've spoken to artists who've been to the Antarctic or so with NOAA. And I think it's always worth asking. Of course, and I don't think Ocean X do this, but other organizations that I've worked with, working on coral reefs, for example, they have a business model actually where they have paying customers to go to places that you wouldn't normally be able to get to, like very remote reefs out in the Pacific Ocean. And the money paid by I think tourist is the wrong word, but the people who are not the
Yeah, I wouldn't
scientists,
use tourists. Yeah, it's like the highly interested. Let's just say that.
the money paid by the highly interested allows a couple of berths on the vessel, to go to
Right.
scientists, which enables access. So there's several, there's many different
So, Sam,
models
the
for
reason why I
this.
bring that question up is sometimes the highly interested may not be a scientist, but they may be an avenue for future funding
Yeah,
through their network and
yeah.
syndicate.
So yes, I mean, I think it's always worth a conversation, and if you see opportunities like that, I'm happy to talk to you and connect you, certainly to my network of people who do such things.
Thank
Well,
you. Solid.
thank you. That's interesting and cool. But Robert, I hope you get to go on such an expedition.
Yes.
Please make videos and share. I'm not sure if I will. Yeah. Anyways, but thank you so much for your time. Part, did you have a last
Yes,
comment
yes, yeah.
to?
So I was very intrigued by the conversation that Sam was having with in response to the points he made in response to Kyle's question. So Bruce Damer was one of our colleagues. He and Dr. Dave Deemer, they
Mm-hmm.
are some of our former colleagues. So in 2019, a paper came out. It is called The Emergence of Life. It was published in the Space Science Reviews. I'll be more than happy to share that paper with anyone who is interested. So
Mm-hmm.
that paper covers the various dimensions or various ongoing hypotheses about the origins of life.
Mm-hmm.
Primary amongst them are the hydrothermal vent origins of life, and
Mm-hmm.
then the competing hypothesis, the pros and cons of each. Now, it's remarkable that I'll just paraphrase what Jack Shostak, who works in the RNA work, he's a Nobel laureate from, I think, Harvard, right? So
Mm-hmm.
he gave a talk a few years ago where he said, it is time that we should consider given the harsh conditions of the alkaline conditions of the hydrothermal vent ecosystem, we should consider alternate hypothesis that is more conducive for biomolecules to polymerize. That is where
Mm-hmm.
Bruce Dahmer's theory comes into the picture.
Mm-hmm.
Now, you must be familiar with, I'm assuming you must be familiar with Mike Russell. So
Mm-hmm.
Mike Russell is one of the primary proponents of the hydrothermal origins of life theory.
Mm-hmm.
So in his article, I'll share that article, maybe back channel some of you who may be interested. He mentions twice, I'm just paraphrasing him. We then expose this false requiem being played for the submarine alkaline vent theory for life emergence for what it is, before playing our own overture to emergent life. He then adds, it seems to have escaped our critics that the hydrothermal vent origins is not an origin story, but a theory of emergence of a unique dissipative structure. He himself concludes that the AVT is not an origin story, but a theory for emergence. I mean, one could say that for the other theories too. But the emerging consensus right now is that life most likely originated in those small, tiny islands which may have sprouted during the end of the Hadean, towards the end of the Hadean. In fact, Jeffrey Bada had a fantastic paper on this about how he showed that the tiny islands might have mushroomed throughout planet Earth towards the end of the Hadean, and these environments provided ample space, the perfect conditions for the wet and dry cycles, which Kyle mentioned, referring to Bruce Dahmer's work. So that's the current. These are the current emerging hypotheses. I'll be more than happy to share papers related to these.
For sure, for sure. And you know, I don't disagree with you. I mean, we don't know the answer, and you know, perhaps the only way to find the answer, because you know, unfortunately, the problem is that these early organisms, they didn't leave a fossil record, or even if they did, it may not have survived, unlikely to have survived. You know, the only way we find an answer is to find life on another planet or moon, and take our n of 1 up until an n of 2. But you know, I agree with you. It's a long time ago. 4 billion years is a long time ago, and the planet was very, very different. If you had visited the Hadean Earth, you wouldn't even recognize it as Earth. I mean, it's as alien as any other planet you might imagine, and it's very difficult to sort of you know, to understand what was going on at that time, conditions of the atmosphere and the oceans, and so on. So you know, I think it's a question for the asking, and it's a fascinating one.
Well, God forbid we don't want to go back to Hadean, because the
No, we don't.
UV levels would have been so hazardous we wouldn't survive.
Exactly. Yes. Yes. But good questions.
Yeah, thank you so much. I wanted to point out we had a guest speaker here about his work, how proteins can form actually on stardust, which is really interesting. So that adds a little bit more to the puzzle.
Yes. Yes.
That was really interesting. But now, thank you so much for your time, Sam, and for again bringing us along your adventures in the deep ocean, and going the extra 5 minutes
Cool.
that brought us here. And we wish you all the best for your research, all the funding, and many more deep dives. And please come back to maybe share one day some more updates on your research. This was an amazing talk. I enjoyed it so much to be.
Brilliant. Well,
Yeah.
Katrina, thank you very much for the invitation, and certainly I would love to come back. It's a great thing that you're pushing here with the community, and it's been a fabulous experience. I'm really grateful.
Great. Thank you so much. And thank you everyone for coming, sharing comments, asking questions. If you like discussions like this, join the club, Science Society. We will have more events like this. Tomorrow we have, a very different topic. It's about IVF and sequencing that can predict the risk of miscarriage. And then we have a new engineered mattress that can improve quality of sleep. They kind of came up with the algorithm, what's the ideal temperature, body temperatures, falling asleep, and then during sleep cycles. And this mattress kind of adjusts to it. It's kind of interesting data that they went through. And then on Friday, we'll have Dr. Ren and Dr. Chen talking about the new semiconductor material that is better than silicon. They join us from MIT. So again, thank you so much, Sam. This was amazing. I enjoyed it so much. Enjoy the rest of your day, and hear you
Thank
all
you,
next time.
Katrina. Katerina. Thank you, Katerina. And Sam, FYI, I know you're new to the app. I sent you a message. If you look at the little pointy arrow up to the right, click on that. You'll see a message in there, okay? Thank you.
Okay. Okay. Brilliant. Okay. Thank you so much.
Thank you, and I'll close the room in 3, 2, 1. Bye, everyone. Thanks.